everyone. Welcome to our talk. Thank you so much for coming. I'm sure it's been a long day, so hopefully it doesn't feel too long. So here's our talk, Flink on Karmada, building resilient data pipelines on multi-cluster Kubernetes. We'll guide you through the journey that we went through to support stateful application failover on Apache Flink, and the collaboration that took place between the Karmada community as well as the Bloomberg Streaming platform team to add this support. Hopefully by the end, you'll have followed along, been introduced to the Karmada project, and learned some of the basics about how you can improve your data pipeline resiliency as well. So starting with introductions, my name is Michas Szacillo. I'm a senior software engineer and tech lead at Bloomberg.
My name is Li Wang, and I'm also a software engineer from Bloomberg as well.
Together, we work on the streaming platform team, which provides Apache Flink to many different users within Bloomberg.
Do you want to describe the agenda? Oh,
sorry. For the agenda today, we'll start with a condensed overview of Apache Flink for those who might not be familiar, so we can provide just more context for you as it's the main point of our talk. Specifically, we'll touch a little bit about the importance of application state and the recovery mechanisms that are already provided by Apache Flink. With that background in mind, we'll review some of the challenges we faced with managing Flink applications in a multi-cluster environment while ensuring resiliency, and how we were able to use Karmada to support automated and stateful cluster failover. Finally, we'll touch on the overall benefits of Karmada, the outcomes, limitations, and further improvements we're working together with the Karmada community to improve.
so at Bloomberg, we operate a large-scale streaming platform that empowers critical financial data processing. We currently have around 1,000 unique Apache Flink jobs running on top of multiple Kubernetes clusters spread across multiple tiers. These Flink jobs handle a variety of use cases, including data ETL, real-time analytics, and event processing. To give you an idea of its impact, this system is crucial to Bloomberg's core financial products, which provides real-time market insights to traders, analysts, and financial professionals across the world. This image here showcases the Bloomberg's terminal, which is where the process data is visualized, helping our user to make the informed decision in real time. Given this scale, ensure reliability and efficiency is our top priority. This is where Flink on Karmada comes into play. So what is Apache Flink? Apache Flink is a popular open-source data streaming framework. It has features including low latency, flexible and high scalable to process massive amount of data. It also has exactly once guarantees to ensure data integrity. Last but not least, it comes with a built-in fault tolerance and a state management system to maintain reliability in distributed environment. Flink job often runs continuously, but what happens if a failure occurs? To ensure reliability, Flink uses state snapshots, including checkpoints and save points. In case of a failure, Flink can automatically restore from the latest state, minimizing data loss and downtime. Here is an example. The events get ingested from an event log into a Flink application, and internally, this application periodically writes checkpoints to a persistent storage. If a failure occurs, Flink restores from the latest checkpoint to ensure seamless recovery. Now that we understand Flink state management, let's talk about job deployment on Kubernetes. Apache Flink supports Kubernetes natively, which makes deployment scalable and manageable. The Flink operator automates job lifecycle management, including job deployments, upgrades, and auto recovery. Here is how it works. The user submits a job YAML file to Kubernetes, and then the Kubernetes API server processes the request. Then the Flink operator deploys, upgrades, and monitors Flink jobs inside the cluster. You will finally get a fully managed Flink job running on top of Kubernetes. In distributed environment, failures can always happen, but Flink is built to recover gracefully. Using the HA settings, Flink can recover from cluster internal issues such as hardware failures, pod crashes, or transit network glitches. In this diagram, on the left side, we see a normal job execution. The user code interacts with the local state backend, and state is persisted as a save point into a distributed file system. If a failure occurs and the job crashes, the persistent save point is still there. On the right side, when the job restarts, it reloads the save point, restores state, and continue as if nothing happened.
So, as previously mentioned, the streaming platform team manages many different Apache Flink applications. And as the platform grew, we started to encounter some challenges in scale. So most notably, control planes are currently tied to a single cluster. And given that our platform spans multiple tiers with users deploying many different jobs, as the number of jobs grew, this starts to become quite cumbersome. Users have to keep track of the clusters they're deploying to. They have to worry about whether the cluster has enough resources to host their job. And they have to manage a bunch of kube configs in order to set up their CD pipelines. Additionally, once these jobs are actually deployed, we expect them to be long-running and actively processing data. But given the nature of long-running jobs, failures aren't something that could happen, but they're something that will happen. Apache Flink luckily provides a lot of coverage for dealing with these types of intermittent failures with its high availability support. But high availability runs on the assumption that recovery will take place within the same cluster. Let's take the Kubernetes high availability as an example. The metadata that Flink will write to the config map will point to the latest state that was published by the Apache Flink application. But if that config map is deleted and the job fails, the Flink operator will be unable to reconcile what the latest state actually is, and it will ask the user to manually reapply the job. Finally, this means that cluster failover itself at the present moment is a manual process. If a cluster goes down, we get alerted of this, and tenants will either have to have their own high availability setup in place, so either running two different pipelines in tandem in different data centers and double processing, or they'll have to manually redeploy their job to a healthy cluster. This can be a bit cumbersome because users will have to understand what their latest state is, and as the number of jobs grows, this can get quite error-prone. And then lastly, the maintenance windows that we do on our clusters become very expensive and require coordination. Given that Kubernetes updates quarterly, that has a lot of maintenance windows in 1 year, so each time we have to migrate users off. So given these limitations, what does our ideal control plane actually look like? Well, we wanted a unified control plane that would require users to have, or require users to only use a single kube config and apply their jobs to a single place. Secondly, once these resources were applied, the control plane can handle the logic of intelligently actually scheduling these applications to one of the clusters in the federation, keeping in mind available resources or node requirements. And then finally, we should also monitor the health of both the Kubernetes clusters and the individual applications that have been scheduled. If the control plane detects some sort of issue with the cluster or an application, and it stays unhealthy for a prolonged period of time, we should try to reschedule the application to another cluster. So as we started to solidify this ideal version of a central control plane, we started to research some potential options that were in development. This is where we were introduced to the Karmada project. Karmada is an open source Kubernetes management system. It's built to manage cloud-native applications across multiple Kubernetes clusters, and it comes with a variety of helpful features that users can tune and tailor to their specific use cases. It allows platform owners to manage groups of Kubernetes clusters from one place, minimizing the operational overhead of dealing with many, many clusters. It gives platform owners the ability to define their applications and how they should be scheduled to clusters within the federation with advanced features, including resource-aware scheduling, as well as cluster affinity rules. Karmada also provides a unified authentication endpoint, as well as a unified endpoint for viewing resources and managing applications. And finally, what we found most interesting was the support for automated cross-cluster failover, which is something we're talking about today. So in order to understand how automated failover works in Karmada, we wanted to go over how Karmada actually tracks both of these things. So for cluster health, Karmada relies on calling the existing Kubernetes health endpoints. In response, if it determines the cluster is unhealthy after a certain grace period, it will do a taint-based eviction and reschedule applications to a more healthy cluster. For application health, it's a bit more granular. Karmada provides a framework for defining resource interpretation, so users can define how they want their application to be treated, whether it's healthy or unhealthy. So this diagram represents the first version of how we used Karmada to manage and deploy our Flink deployments. So users would apply their namespace jobs to the Karmada API server endpoint. We automatically provide the necessary propagation policy on their namespace. So for those unfamiliar, propagation policy is a custom resource defined by Karmada, which tells Karmada how you'll actually schedule the application that the propagation policy is scoped for. So in our case, for example, we set some spread constraints on the Flink deployment since we want it to only be scheduled to a single cluster, and the replicas will be scheduled together. So we set that to be max 1 cluster. Now, once the application is scheduled successfully, the Flink operator picks up the deployment and schedules the job, after which point the full status will be available on the Karmada API.
Now let's talk about some of the limitations we faced initially when integrating with Karmada. First, for the application failover to work, Karmada must understand how to interpret the resource health. However, using default settings, Karmada doesn't have any awareness of Flink state. This is an issue when it comes to rescheduling. And second, when a Flink job is rescheduled to a new cluster, it needs to start from its previous state. But the state is not preserved during failover. That means the deployment will be started from scratch, which isn't ideal for a long-running streaming job. These limitations motivate us to explore better solutions for state management and failover. And to get a better solution for failover, the most important thing is to understand the job health. Flink maintains its own internal job state machine, and we have drawn a simplified diagram attached on the right side. So how do we interpret it? If a job is in the running state, here we filled with a green color, or in any of the terminate state filled with a gray color, like failed, finished, canceled, or suspended, we consider this job as a healthy state. But if it is in one of the blue ephemeral states, like reconciling, initializing, or created, we have to be more careful. If there is no user error, like bad image paths, we treat it as healthy and don't trigger a failover. But if the job is stuck in one of these states without a no error, we treat it as unhealthy. And finally, we have the yellow-colored, short-lived state like restarting, failing, and canceling. These are part of normal transitions and will quickly lead to a terminal state, so we treat them as healthy as well. Let's take a look at what is a healthy state transition. Usually, a healthy Flink job starts with a reconciling state, where the job manager isn't scheduled or hasn't reported the status yet. And next, it moves to initializing, where the Flink components are starting up. And then it reaches created, meaning the cluster is ready, but the job is not processing data yet. And finally, it enters running, where the job is fully operational and processing data. Here is another example of an unhealthy state transition. As what we saw before, the job is in the running state and the processing data. Everything looks good, but then it suddenly transitions back to created. This usually means something went wrong. Maybe task manager crashes, or the cluster itself has some internal issues. So by checking the job state, very likely we can tell if a job is healthy or no. However, there are some edge cases that checking internal job state is not enough. We also need to look at the error field inside the state for deployment issue, including misconfigurations, such as bad container images or malformed YAML files. Also, it can come from runtime problems such as application bugs or bad upgrades. This is what Michas showed before on how we run Flink on Karmada. In addition to the previous propagation policy, we add a failover field in the YAML. With this change, if a deployment becomes unhealthy, Karmada will wait for a threshold we configured and then purge it right away for rescheduling. So was that a successful failover? Not exactly. Although Karmada detects the job failure and reschedules the job, it always starts as new, which means we lost the running state. In Flink, however, to gracefully resume after failure, we need the latest checkpoint. And also, to get that, we need to preserve the job ID across clusters.
So as Lee described, although Karmada was correctly detecting application and cluster health now, the failover wasn't yet complete. We still needed a way to figure out how to conserve information from the previous job so that the new job could have a reference as to where to start up from. After working with the community, we came up with an idea of a state preservation enhancement, which extends the existing failover API, and this is set directly in the Karmada propagation policy. It consists of two fields. The first is a JSON path, which is just an expression that identifies the specific piece of data that we want to conserve in the status, and then an alias label name, which is just going to be the name of the label. So as you can see, the propagation policy on the right shows this new API in action, with us selecting the job status job ID field, and then injecting this information as a label into the newly failed over Flink deployment. Now there's one last step here. Even though the metadata itself is injected as a label into the Flink deployment, we still need to convert it into a way that the Flink deployment can actually consume that information. So we were already using Kyverno webhooks for validation and mutation. For those unaware, Kyverno is a policy management tool which allows us to declaratively define policies that can validate and mutate watched resources. So we decided to reuse it and implement a mutating webhook that could inject the necessary initial save point path and point to the latest state from the previously failed job. So here is the finalized diagram of how we did failover. So let's assume that we had a job successfully running on cluster B. At some point in the future, the application suddenly transitioned to a reconciling state. This means that either the job manager crashed or the operator is just unable to get the status from the application due to some sort of issue. Karmada will treat this application as unhealthy, assuming there are no published errors, and eventually start taking down the toleration seconds defined within the resources propagation policy. After the toleration is up, failover will kick in. So Karmada will pull out the job ID from the published job status and then delete the resource on cluster B. Karmada will then inject the state preservation label into the scheduled resource and will point to the previous Flink cluster's ID. So our Kyverno webhook will intercept this request, pull the job ID, and then set the initial save point path so that the Flink operator knows, okay, this application is starting back up from a previous state. Now, there are a lot of benefits here for us. I think the biggest pain point for a lot of our users was needing to manage and keep track of a lot of different Kubernetes clusters. So by having a unified control plane, users can apply, update, and manage their jobs from one place with authentication and intelligent scheduling already baked into the setup. The other huge benefit was the automation of cross-cluster failover, which is critical to ensuring data pipeline resiliency. Now, it's important to note that cross-cluster failover should be a rare occurrence. Apache Flink's high availability feature is expected to generally handle job failures that occur within the same cluster. And so generally, applications should self-recover. This is really only for cases where there are exceptional circumstances, such as a partial or total cluster failure. In those cases, it saves us as platform owners a lot of time and also allows users' application to auto-recover in a healthier cluster without their explicit involvement. Following that vein, different users can have different failover requirements, so it's really great that these failover definitions are flexible and configurable, as some users might be more sensitive to failover, whereas others are okay being more conservative. But as a whole, automated failover has helped remove a lot of the operational burden that comes with managing our platform on a day-to-day basis. And additionally, maintenance windows no longer require heavy coordination. We can simply evict applications from a cluster and have them restart in a different one. And it also provides us with the ability to DR test out of the box. So how would you go about generalizing this and trying out the feature yourself? So luckily, Karmada already provides resource interpretation for most native Kubernetes resources, such as deployments or stateful sets. But if you're using a CRD, you may have to define your own custom interpreter. Luckily, doing so is pretty easy. All you have to do is fill out the custom interpreter interface with several different methods that you think are applicable to your use case. So for example, you could fill out the get replicas method, which tells Karmada how many replicas your CRD will schedule along with the resource requirement. Or you can fill out the interpret health method, which Karmada will use to determine when your CRD is healthy or not. Secondly, you'll need to determine how you'd like to configure failover. So how sensitive Karmada will be at detecting issues and triggering a failover. How quickly do you need applications to be purged from the cluster? Do you want them to be deleted immediately, or do you want some grace period? And is there any state that you need to conserve between failovers? Lastly, once this state is actually injected into your resource, you'll have to find a way for the member clusters to actually consume it. In our case, we used a webhook to inject the initial save point path in the Flink deployment spec. Now, there's some existing limitations and pending improvements with the features that we've talked about today. So with application failover, this is still a developing feature, and the Karmada community is continuing to gather more use cases to better understand gaps in the existing implementation. So for state preservation specifically, this feature was added recently in version 1.12, and we want to encourage more users to try it out and see if it fits their needs. From the perspective of failover itself, there are 2 points to consider. The first is the toleration seconds needs to be tuned carefully. So toleration seconds kicks in immediately after the resource has been scheduled to a cluster. So you don't want to set it to be too low. Otherwise, Karmada will continuously try to reschedule your application if it never reaches a healthy state. So this means that toleration seconds itself is limited to be greater than the application's initialization time. We're working with the community to see how we could change this, potentially only taking toleration seconds into account after the application transitions to healthy for the first time. And then additionally, the health interpreter is only really meant to provide an estimate as to whether or not the application is unhealthy. For most cases, we assume that if you're in a reconciling state or created state, your application isn't actively processing data. And so if there is no error there, we assume that there could be some sort of cluster issue causing problems. Lastly, cluster failover itself is currently undergoing improvements. As a result, the state preservation feature has not yet been made available there, but keep your eyes out. This support is supposed to be added soon. Lastly, for the Karmada community, wanted to add a little bit of a plug. We're a very active community, so if you'd like to contribute, please reach out to us on Slack or on GitHub. And we're also presenting further at KubeCon. There are 2 other talks that are going to be given tomorrow, so I encourage you to attend those. And if you'd like to talk to the community in person, we have a desk in the project pavilion. I think the kiosk number is 4B, and we'll be there in the mornings.